As part of our cloud on-ramp effort, we want to go behind the scenes a little on some interesting projects relevant to cloud computing. So today I'm talking with Loic Bachelot, who's a data scientist at Crescent at the University of Oregon. So Loic, thanks again for agreeing to chat with us today.
Yeah, thanks for having me here.
So you led a team that published a paper in Seismica recently on a denoising method for GNSS data in the Pacific Northwest with the goal of better capturing like subtle slow slip events that can be lost in the noise otherwise. That noise being caused by things like atmospheric and ionospheric conditions along the path from the satellite down to that GNSS receiver. And you used a machine learning method called a graph neural network, which is what we want to get into here shortly. And if I'm wrong about any of those things, you can correct me when we talk about it. And the idea was to identify noise affecting kind of multiple stations similarly at the same time by using that. But before we get into that, let's start here. One thing I like to ask people about when we do these is how they figured out how to do this, if this was their first time working with such a method. And I think that's not the case with you. You have a lot of experience with this. So I wanted to ask, how did you get into working with big data and machine learning in earth sciences?
Yeah, my background is in data science. Really, I have a master's in AI and big data, so I have no background in earth science originally, so come from the other side, if I can say it that way. And I started applying machine learning methods when I was back in France at Ifremer in oceanography to predict water temperature for the full column in the Gulf Stream area. And we used a very simple neural network for that problem. But that's how I got into applying these cutting edge machine learning methods to earth science problems. And yeah, I got introduced to more slow sleeps when I moved to UO here, working with Amanda Thomas and Diego Melgar. Um, yeah, that's how I got into this.
So let's talk about this paper. Let's start with kind of the technique itself, which people can get more info about by diving into the paper itself, and we'll talk a little bit more about kind of the behind the scenes stuff after that. But can you just explain a little bit about how this specific GNN method works and where the idea came from to use it for this problem?
Yeah, I think you made a good point in the introduction about what are the different source of noise, and this is where really trying to find a solution came from. With these source of noise that are spatially correlated across multiple stations, there must be something that we can do to leverage that. And this is where using not only a neural network at one single station, if you do that, you're missing that opportunity to leverage that the neighboring station also has that noise to be able to extract it and remove it. So this is where we're looking into multi-station approach. And then we're working in the real world. So our stations are not a perfect grid. So therefore using a CNN that is perfect for grid data, such like image, um, might not be the optimal fitting algorithm for our set of GNSS station that is spread really um, heterogeneously across the Pacific Northwest. So this is where using a graph neural network really comes in handy because you don't need to worry about have equal distance in between your station and so on. And other really cool approaches are network of GNSS station is moving constantly. We have new stations as new fundings come. We have older stations that get decommissioned. And the graph neural network can handle that transparently. You just remove the node and your station is gone. You add a new node, new station is there, compared to have as again, the CNN is another option to include more stations, but you are kind of more stuck with that rigid geometry that you define at the beginning of your exercise.
So let me try an analogy and see if I have kind of how this works right. After we're done recording this, I have to edit this together for people. And one thing I might do is apply a noise reduction to the audio, right? Which is there are these machine learning based tools in the software that have been trained on human speech, so it can mute things that don't match that pattern. So when I click a mouse or my furnace in the next room kicks on, hopefully you won't hear that. This is sort of similar, right? Except that you're not looking for like a generic signal pattern to preserve. You're looking for a like a pattern of shared noise that's varying over time that you're going to remove.
Yeah, so thinking of a sound approach, what happens with probably the algorithm that you're using is knowing that certain frequencies are not a part of speech frequencies, so you can just simply remove that. And that's what's being applied for maybe more high frequency noise. But the idea with our algorithm would be more if you have someone speaking super loudly, it's the exact same frequency as you, except you're the closest one to that microphone. And if you have 10 other microphones in your room and you remove what all of the microphones have in common, you might be able to remove that loud sound. And the thing that's left at your microphone is only your voice. If we stop in time and we think about one station only, this station, we connect it with the edge of the graph to stations that are further away. And this is how we see, okay, what is in common with all of the stations that are far away, like, too far to be seeing the same signal of interest, but they're still correlated. And that correlation is not something that the scientist wants to study. Therefore, we can remove it. And each station has its own sets of connection of other station. Um, Here's where it gets complicated because one station is also the helper station of another one at the same time as we denoise it itself.
But we're and you again like all machine learning methods, you start with a training phase and then you kind of use that to apply it, which you said you could even do in real time, right?
Yeah, the neural network that we're using um, is very, very small. So the way graph neural network are functioning is you apply some sort of, um, we just have an MLP per station. It's the same MLP that we apply, so we do the same forward for each station. Then we have that message passing layer, which is where the station starts talking to the neighbors. And then we have another decoding piece. This is where, okay, I have my own information, I have the information from my neighbors, now I'm decoding what is noise. And this simple network that you apply at each station are the one that we used is very small, so it's super fast to run. And it runs in parallel across all of the 500 stations of the network. So it's not, the forward is very, very fast to do. The training is where it gets a little bit more tricky because we used a masking mechanism to kind of duplicate what is used as a dropout in if we're thinking of a single neural network approach to kind of help generalize the network if we have unstationed out, that type of thing. So we used a masking mechanism to train only on 30% of the network at each time. And this is where this becomes a bit more consuming for the training phase itself. But with the size of network that we used, we were still pretty reasonable in my opinion, meaning around 2 hours on one GPU for training. So we had time to iterate because, yeah, with graph neural network, the number of hyperparameters that you need to fine tune is kind of exponential compared to more regular approach because you don't only have to train and fine tune your neural network, but you also need to fine tune your graph itself. I mean, like, how long are my connections? What do I put on my edges as connections? How many stations should I connect together? Is it should I take the 10 nearest neighbor with a threshold of at least 400-kilometer distance is what we landed on. But this comes with a lot of fine tuning to not predict signal of interest, still predict noise. And do you use 10? Do you use 20? Do you use the entire network? There's always trade-offs there. So there's a lot of fine tuning. And as soon as you fine tune your graph, fine tuning your algorithm itself, the machine learning piece is still there to do. So there's a lot of iteration piece that comes to do.
One thing I thought was interesting in this case is that You mentioned in the paper there are some non-machine learning tools that exist to do this task, and so you compared the results with those to some extent. So, what did you learn? What was the result of comparing those different methods, and so why might you choose one over another?
Yes, I think the timing of our paper actually is what drove us to really push in that comparison, because at the time when we started the study, there was not that much application for those filterings. The Dawinski paper was prior to 2000, so it's not a recent method, and the application was to extract the differences between stations for a very small area. So you can think there was an earthquake, you have a station on each side of the earthquake. How do they behave differently? But not trying to extract their absolute position of these two GNSS stations. And so when we were thinking at the bigger scale, we did not think that this was a comparable algorithm. But quickly at AGU 2023, there was a little controversy around Quentin Bletry paper with earthquake precursors. And they applied some denoising in this paper. So we thought, okay, let's go back and try to apply these. So this is why we compare with the original Dawinski stack filtering, another stack filtering where we constrain to be far away from what we consider events, and then another stack filtering where we apply more of the graph neural network logic with for each station we have a different stack with a minimum threshold distance for the stations that we include. And yeah, I think he ended up adding a ton of value to this study because the results were interesting, meaning graph neural network was performing comparably to the others. So at least it's not worse, that's good. But the others are still very competing methods and much, much easier to implement and put in place. And so the discussion section of the paper, we go over what would be our recommendation of when to use each. And all of them have pros and cons. So the basic Dawinski filtering is amazing to extract differences between stations. So if this is what you're studying, this is what you're looking for, there's no need to look further. This one is perfect to compare one station to another. But yeah, no absolute values of position using that filtering, you're not going to be able to because you're removing signal. And when you think at slow slips, you have maybe sometimes more than 50 stations that are moving the same way due to the slow slips, and that's going to end up in your stack. So therefore, you're removing that signal. So the second approach, using tremors as a proxy of where is your event, I think is quite valuable when you are studying one specific slow sleep event that you already know of. But the problem is you need to know about it beforehand. And the definition of what is far enough from the tremors, I think that is not as simple to answer as, okay, it's 50 kilometers. I I'm not sure exactly what comes into play to defining this properly, but I still think that this stacking using tremors can be really valuable to simply remove noise anyway. And with the last approach, we found that um, the maximum size of the stations that you include also has an impact on your denoising. So we were focusing on the Pacific Northwest, so that's pretty big area, but we're still not full North America. And if you think full North America, you might have the full East Coast telling you your stations are moving west, full West Coast moving east, and therefore your stack ends up being zero, and you don't remove anything. So have this approach with a maximum distance think like added to it can be a good approach as well. And this is where the graph neural network kind of works great across the board. Does not especially outperform the other methods, but in terms of flexibility, I think has a lot of value there.
All right, so let's go behind the scenes then of things that aren't in the paper. Um, what did it take to organize all the data in this case and actually run that analysis? So you ran this on a local cluster at Oregon, right? But can you like walk through that workflow and kind of all the work you had to do just to get it to run?
Yeah, luckily GNSS data is not the hardest to gather. We have good data centers uh, through Earthscope and through University um, Nevada, Reno. They also have a good data center there, so it's not that difficult to get. So that first step, I felt pretty lucky. Uh, Second step is building the graphs, and that's all done with PyTorch Geometric, and it can get a little bit more challenging. And yeah, working with sorry, just backing up a little bit, working with the daily data was also easier because in terms of size, it's pretty manageable. We attempted and tried a little bit on the higher rate GNSS data, but this is where more size issue would come into play. So I'm not sure I'm going to have something super exciting for you in terms of big data management with this paper, but that could become an issue if you're working with higher rates for sure. The first step of building the graph, normalization of the data is important as for any machine learning algorithm. And then training now is, I want to say, fairly easy nowadays with PyTorch Geometric, and it's an option to run on GPU. It's super easy. I remember a little couple years ago when you had to more manually deal with CUDA and such. Now it doesn't feel as daunting to try and run on GPU. Um, and so all of this was done on our HPC here at UO. And then I used a lot Jupyter notebooks for doing quick analysis of the results and quick visualization. And all of the code for preparing the data all the way through training and even the inference steps are available on our GitHub.
And I noticed in there that you built that flexibly to parallelize on CPU only machines or on GPU. So and I know you said this isn't like the biggest big data job, but how does that play into like how quickly or how well this runs? What are some of the benefits of getting that out on GPU cores instead?
Oh, it's really massive for graph neural network. I think you divide the time by at least 20 compared to CPU only. And yeah, we do have NVIDIA A100 at UO, so it's a decent GPUs, but no, CPUs are not as good for parallelizing across for the graph neural network because, as I explained earlier, you apply a very simple neural network for each of your node in your graph. And applying this in parallel on GPU, this is where the value is enormous because you can do your 500 station in one clock, basically.
So you said the training runtime was pretty short on the cluster. I don't know how many machines you had working on it, but if you had tried to run that on like a single computer on a laptop, how much longer do you think that would have taken?
Uh, on laptop CPU probably would take a longer overnight training. Yeah, yeah. And the cool thing of being on the cluster is I was still doing single GPU training, so not crazy across GPU, but I was doing multiple runs at the same time to try different hyperparameters. So I did not really try to have the fastest training possible, but still trying to be efficient. using more.
I mean, one of the things we're obviously working on with our data archives at Erscope is optimizing them from the cloud. So we moved everything up to like cloud hosting, but now we're trying to work on how do you make it so that you can, rip that stuff off the shelf in a cloud server and then just immediately go run your analysis adjacent to it rather than having to download it all. So, I said, or you said you were working with daily position data and it got kind of unwieldy if you were trying to do, I don't know, down to 1 hertz or something. But if you that workflow where you might be able to query, say it's the 1 hertz, just out of whatever stations you want based on whatever attributes you want, and then not have to download those daily Rhinex files to something, and then be able to go run it on GPU cores or a bunch of GPU cores right next to it. Like, how do you have a sense for how much of a difference that would have made? Both like, and it might be a little easier, right? But or a little faster, but would it also have been required like big changes to the way you coded that up, or would it run pretty much the same?
Mm, I think it's a four-piece question you had there.
Yeah.
With the way it runs, I think it's not that different because you can easily containerize things nowadays, and then you can launch that on AWS fairly easily. The question that I have now working for Crescent, we also work a lot. I mean, we collaborate with you guys on our AWS as well. A question that always come up is it cost efficient as well? When we're working in academia and here we have access to an HPC, if you're running a lot of training, AWS is gonna be costly too. Like those GPU hours are stacking up fast, let's say. And so then you start having the trade-off. Okay, is it more expensive to move the data or to do my training over there? So I think for a machine learning project, that is a question to look at. Um, in our case, data, as I said, we were working with a daily, so it's pretty small. So the question of moving it was not really, it was pretty fast to answer, let's say. Um, but then you can think about it in two steps as well. You have your training, and once your model is trained, what do you do with it? And then, yes, the inference for sure would do that on clouds because downloading the data would become what's the longest and what's the most costly because the inference is instant and AWS has products such as Batch, for example, that would be perfect to run across, query the S3 bucket, and yeah, so multiple questions to think about before going all in on the cloud is my take on it.
That sounds consistent. Yeah. Um, all right. Let's maybe finish up on a big picture question, and again, I'll make it like at least 4 questions for you. Um, a lot of people are going to come at this with less experience and be looking for ways to do these things, right? Or like not know where to start. Or so I'm just curious where you look for new machine learning techniques to use. Like, are you sort of reading other papers in inner science or in other fields and just getting inspiration that you want to try out? Are you starting from the scientific problem and looking for a machine learning technique that fits it? Or are you doing that the other way around? Are you finding a technique that you think works really well and then looking for the kind of hard problems in science that it might be able to solve?
Yeah, that's a really good question. Luckily, my background being in AI, my former friends from school are still in the field, so they can always text me new things. But one thing I really enjoy is looking at what is being done in adjacent fields. So climate science is very advanced in things like that, in handling big data. I want to say they might be a little bit ahead of what we're doing in earth sciences. And so looking what they're doing, what algorithm they're using, how they're handling their massive data is always very valuable to see new methods. Is this transferable to what we're doing? Or maybe it's completely different. And especially in our times where we have more and more remote sensing, I was doing oceanography before. Remote sensing whether you're looking at the earth or the water, in the end, you might be actually looking at something quite similar. So maybe the algorithm, you can reuse it. So trying to expand what you're looking at is a good approach. Staying curious, and we're lucky at University of Oregon that our Earth Sciences seminars are quite broad audience and quite broad speakers, so we also are exposed to a lot that way. But at conference is a good point as well. At AGU, if you don't have a session you're especially looking for, maybe go attend a random machine learning one on whatever topic, and you'll be, oh, that algorithm is cool. Maybe that would transfer to what I'm doing. I think is a good approach. Looking fully to what is being done in the more machine learning conference, I'm not fully sure because it's really more cutting edge, and we're more doing applied machine learning, which in my head, I have a little separation between the two. We don't fully invent algorithms in our field. We more use what has been proven to work. And so looking at the latest generative AI might not be where you want to look at.
And so we might feel like we're on the cutting edge here, but really we're waiting behind the cutting edge for useful things to come over, and there are wilder frontiers out there that you might not want to get involved in.
Yeah, if we look at the reference from my paper that are pure machine learning, there's nothing that recent. I guess everything is at least 10 years. So a graph neural network is fairly new, and I think is a perfect example of we don't have any grids in our domains. Our stations, even seismic stations, are not gridded data. So that's really something that I see pushing in the future in our field. And it's Ian McBurty that has really good application of graph neural network in the seismic world.
All right, well, we'll wrap it up there. So, Loic, thanks again for your time today. The paper we talked about is linked in the description, complete with that nice GitHub repo that you mentioned. You can go check that out. And you can find information related to the Cloud On-Ramp project that we're doing here at Erscope on our website at erscope.org/data/cloud. But for now, thanks for watching.